Hello everyone. So we are in the last question number 12 on this particular series. So let's get started. And this is all about complex numbers. So first, there is a complex number which is given in the form Zn equal n square plus n plus 1 plus I, and n belongs to natural numbers. Find argument of Z0. So when n is 0, which means here from 0 to like positive integers, 0 to infinity. And org Z0, it's very simple. First, you find what is Z0. It's 0 square plus 0 plus 1 plus I, which is going to be Z0 is 1 plus I. Argument of a complex number will take this form. Argument of like a complex number A plus IB is tan inverse B by A. So the same thing when apply. So argument of Z0 is tan inverse B. That is imaginary part. Don't include the I, just the part, the coefficient of I in simpler terms, B by 1 by 1, which is 1. And what is tan inverse of 1? That acute angle. It's the first quadrant, right? So it should be written in this form, pi by 4. So this is the argument of Z0. And that's simple. Pi by 4 is the answer. Next, B part. Argument of Zn should be expressed in this particular form. That is in terms of n. So let's start with Zn. Zn is n square plus n plus 1 plus I. So what is argument of Zn? Tan inverse imaginary part over real part. Imaginary part is 1, not I. And n square plus n plus 1. This is argument of Zn. No particular value here. And moving forward, so next part is when Wn can be represented as a product of the complex number Z0 times Z1 times Z2 and so on Zn, n belongs to n. We need to prove the first part is arc tan A plus arc tan B equal arc tan A plus B. So arc tan is nothing but tan inverse, right? So I'm going to use tan inverse for the simplicity. And let's start with this. Okay, so arc tan A plus arc. Let me start with LHS and I will use some logical stuff and we will end up with the RHS. So take LHS, it's tan inverse A plus tan inverse B. Okay, I know tan, I can express in this way because I want to convert into the argument form here. So tan inverse A by 1 and this can be written as tan inverse B by 1. We know that argument of like A plus IB can be written as tan inverse B by A. So tan inverse A by like a reverse way. So tan inverse A by 1 means it can be written as argument of a complex number which is in the form A plus 1I, which is just A plus I. And this can be written as argument of B plus I. Right? And we're going to apply a property here too. That is, we know that argument of Z1 plus argument of Z2. It's a kind of a log related thing. It will be combined as you can condense this as argument of Z1 times Z2. Same thing. Let's apply. So this will go like this, which is argument of A plus I times B plus I. Right? And we can go ahead. So this can be simplified as argument of multiply the complex A with, it's like normal FOIL method. A and B will go AB and plus AI plus, then you just multiply I with this and this. So this is BI plus I square. And simplify further. This will go argument of AB minus 1. They are real part plus A plus B whole power I is imaginary part. Okay. And now argument of like something, this is X and yi. So again, argument of x plus yi means you can write it as tan inverse y by x. And here, AB minus 1, also they have mentioned AB is less than 1. So it's a negative part. It is in quadrant 2. But whenever I'm expressing this argument, like this is tan inverse of A plus B divided by the imaginary, the real part we will put actually. But this is a negative. We only take the positive. So you just switch the term 1 minus AB. Since AB is less than 1, this is the valid format here. And yeah, so I started from the LHS, which says that R tan, like tan inverse for the simplicity, A and tan inverse B. And we start from here and then we end up with the RHS. So hence the proof. Very simpler one. And we are moving to the next part. Okay. So next, prove that arc W1 equal to arc tan 2. That is tan inverse 2. Okay, I'm going to start with W1. W1 is, this is the WN definition. WN is W naught, W1, wait, not this. It is Z naught, Z1, Z2, and so on, Zn minus 1, Zn. Okay, so W1 means it's Z naught times Z1, right? So let's frame the complex number W1 here. W1 is, okay, what is Zn then? That have this form, n square plus n plus 1 plus I. So Z naught is 1 plus I, this we already calculated. And Z1 is, let me solve it here. 1 square plus 1 plus 1 plus I, which is 3 plus I. So this is 3 plus I. Got it? And let me product this. 1 times the 3i, 3 plus I is 3 plus I. Then I times, if you do 3i plus I square, this will go 3 minus 1 plus 4i, which is 2 plus 4i. That's simple. I know what is W1. Now we can proceed with argument of W1. So next part is over here. Argument of W1 is nothing but argument of 2 plus 4i. And we know it goes like tan inverse imaginary part by real part, which is tan inverse 2. And the other way of saying is arc tan 2. Argument of W1 equal to, hence the proof. Right? That's simple. And every time when you're solving the question, just go back and check what are the conditions. Even if it is not related in mentioned in part B, it might be from the major case or in part A. This will work. That's simple. So next, to prove argument of W, this is the last part, equal arc tan n plus 1. So I just now proved argument of W1 is arc tan 2, which is 1 plus 1. So when 1 is replaced with n, 2 is replaced with n plus 1. So we can just analyze, okay, when it is argument of W10, it's arc tan 10 plus 1, which is 11. Whatever is used here, just put a plus 1 and it's tan inverse of that value. Okay, let's try, let's prove this using math induction. First, in the math induction, like it's kind of domino fall, right? So the first value we need to check, and n is equal to 0 here. This is the first step. When n is equal to 0. What happens to the theorem? Let's check. So argument of W naught is equal to arc tan, I can write this tan inverse 0 plus 1. This is already proved. Tan inverse 1. So argument of W naught is This is what I need to prove. Argument of which can be represented as tan inverse 0 plus 1. Argument of W. So the theorem holds like the statement. Let me make it as P of n for the simplicity. And this will be helpful. So P of n is this. Okay, when n is true is equal to 0, I can prove that argument of W naught is tan inverse 0 plus n. So n is 0, and yeah, the theorem holds good. So P of 0 is true. Okay, when n is 0, the theorem is true. If this step valid, we will move to the next step, which is some random value k. So that's the step 2. When n is equal to what? When n equals k, assume that the theorem is true. We don't want to prove. You just assume it and we can use this stuff. Okay, I don't know whether it will work, but I'm assuming when n is equal to 2, P of k holds good. This is an assumption step. Okay, it's not like no need to prove this, just assume this. That's the second step. Okay, somewhere a domino falls. Okay, so that's the case. Let's go. When n is equal to k, P of k holds good. So the theorem will obey here for n is equal to k. So argument of W, this is my P of n, equal tan inverse n plus 1. Since I have assumed in this way, P of k is true and argument of Wk can be represented as tan inverse k plus 1. This is an assumption, and also this plays an important role. We will use this. Let me name it a star. Right? Okay. So next, third step. Prove if the k dominoes fall, k plus 1 will fall, of course. Then only the theorem's true. So we need to prove this. Need a logical proof things. We have to follow a sequence of logical stuff to prove this. To prove P of k plus 1 is true. Okay. Right. So you can start with LHS. Argument of Wk plus 1 is equal to argument of, how can a Wn can be expressed? They have given here. So Wn is nothing but Z0, Z1, Z2, and so on, Zn. Z minus n and Zn. So this will go like this. Argument of Z0, Z1, Z2, and so on, Zk times Zk plus 1. Okay, you always stop with k. That plays an important role. Now, you treat it as a single complex number and this as another complex number. So how can we write this? We can split this as argument of Z0, Z1, Z2, and so on, Zk. Right? Or you can just mention Wk. When we are splitting argument of Z1 and Z2, it will go addition. When you expand the argument of Zk plus 1. Got it? So now argument of, this is holds true, right? This is proved because this can be written as argument of Wk plus argument of Zk plus 1. And this is a proven fact. You can use the star here. It's not a proven fact, like we assume this. Argument of Wk can be written as tan inverse k plus 1. So you can replace that stuff here. Tan inverse k plus 1. Good. And what is argument of Zk plus 1? We don't have anything to substitute. We have to solve that part. So argument of, what is first of all Zk plus 1? Okay. Again, I'm just giving you the idea of Zn. How Zn form? It's n square plus n plus 1 plus I. So k plus 1 means it's quite bigger. K plus 1 whole square plus K plus 1 plus 1 and then a plus sign. This is what ZK plus 1 representation. Okay. This is tan inverse K plus 1 plus. This can be written as this is the real part and this is imaginary part. Tan inverse, argument of a complex number is tan inverse imaginary part, which is 1 divided by this part, K plus 1 whole square plus K plus 1 plus 1. Now it is in the form tan inverse A plus tan inverse of this stuff can be considered as B. And we know that we have proved in the same problem tan inverse A plus tan inverse B can be written as tan inverse A plus B divided by 1 minus AB. So we know this and we can substitute that over here. So it is going to be like, let me copy the step and we can follow here. It needs some space. Let me write it over here. And what about the left side? We are working on argument WK plus 1. Argument WK plus 1 equals the single tan inverse B by A, right? Sorry, tan inverse A plus B. So this A is K plus 1 plus B is 1 divided by K plus 1 the whole square plus K plus 1 plus 1 and divided by 1 minus AB. So which is, let me expand this bracket. Divided by 1 minus A is K plus 1 times 1 divided by K plus 1 the whole square plus K plus 1 plus 1. Now it's time to simplify this. So just cross multiply this over here and you will get tan inverse and a big bracket over there. K plus 1 is already there and this is going to be multiplied. The denominator K plus 1 square plus K plus 1 plus 1. We can make it as K plus 2, but anyways, let's keep it as it is. Plus 1 divided by K plus 1 the whole square plus K plus 1 plus 1. Then this division, actually simplifying the numerator part is only done and there is a major division. So you can just put a division like this and you can continue over there. Okay, now I'm going to simplify the denominator. Let's move a little over here. Right. And this is going to be, yeah, again, cross multiplication. This K plus 1 will go there. So I will get, this entire thing will get multiplied to the previous term. So 1 into the same thing will follow. K plus 1 the whole square plus K plus 1 plus 2. Then this stuff and then a minus K plus 1. Okay. Divided by K plus 1 the whole square plus K plus 1 plus 1. And this is the bracket. You can close it. Now, tan inverse. Let me take this over inside. So K plus 1 the whole cube plus K plus 1 the whole square plus K plus 1 plus 1 divided by, this is the term we have, K plus 1 the whole square plus K plus 1 plus 1. And divide change to multiply. This stuff will go there. And denominator, numerator and denominator will get exchanged. So the denominator first I will copy it over there. K plus 1 the whole square plus K plus 1 plus 1. And denominator goes like this. So this will come here, right? So K plus 1 the whole square plus K plus 1 plus 2. Wait. plus 1 it is. Okay. Just a second. Here a plus 1 will come. Kindly change this. And here. Right. And k plus, it's not a 2, it's a 1. Minus of a k plus 1 is there. Now let's close the bracket and this will get cancelled, exactly same stuff. Okay, for the simplification, we got tan inverse k plus 1 the whole cube can be expressed as k cube 3k square 3k plus 1 cube. Then k plus 1 square is like k square plus 2k plus 1. These are simple identities. I'm doing it quick. And k plus 2 divided by. Okay, here what happened? K plus 1 and minus k plus 1 will get cancelled. And we got k square plus 2k plus 1. And I'll read that as a plus 1. Okay. And then let's go. Tan inverse. Numerator is, let me convert into a cubic form. K cube, 3k square and k square, 4k square, 3k and 2k and 1k, or 26k. And then plus 1, plus 1, plus 1, like plus 4. Yeah. Divided by denominator is k square plus 2k plus 2. Right. To simplify it further, actually, what is our aim? I should make it as okay, if it is argument of Wn, I want tan inverse n plus 1. Now I'm working for Wk. I want to make it tan inverse in place of n k plus 1 plus 1, which is your aim is tan inverse k plus 2. So yeah, of course, I have to divide this. Then only it will become a linear stuff, right? So this is our aim. I'm just reminding you. And let's divide. So polynomial division will work here. And here we go. K cube plus 4k square plus 6k plus 4 divided by k square plus 2k plus 2. Let's start multiplying it. And it's just k, right? First term divided by the first term. K cube by k square is k, so put the k in the top. And just multiply this with the whole. You will get k cube plus 2k square plus 2k. And then let's make this. Remove the, like, change the sign for the new stuff. And you will get 2k square plus 4k plus 4. First term divided by the first term again. And I got 2k square by k square is 2. So plus 2 here and multiply it over. 2 times k square is 2k square and 4k and 4. And change the sign, look for the remainder. Cancel, 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 completely 0. So the final answer is tan inverse k plus 2. Right? So where we have started, we started with just argument of wk plus 1. And now I got tan inverse k plus 2. This can be like decomposed into tan inverse k plus 1 plus 1, because this is the form I'm looking for. Whatever I choose here, that plus 1. So yeah, for k plus 1, we have proved this with the assumption of k. Okay, so p of k plus 1 holds good, or you can write true. All the logic things we have applied here. Now, the conclusion is important. For the very first value, yes, the theorem works. When I assume for some random k value that the theorem is working, then it is work for the very next value. This is what the mathematical induction. And now let's conclude it. I'm writing the conclusion here. This plays an important role. Since P naught is 0 or P of 0, so I took the major statement as P of n, right? So since P of n is true when n is equal to 0, it's a kind of domino fall. If the first domino is not falling, then no need to go for the next step. So since first it's working, and next the main thing we did is the assumption. So P of n is true when n is equal. Okay, let me change into P of k plus 1 is true. This, okay, with the help of P of k is true, we have proved. So P of k plus 1 is true when P of k is true. Otherwise, it's very difficult to prove. So with the help, we can prove this. So whenever P of k plus 1 is true, P of k is true, P of k plus 1 is true. This is the process of mathematical induction. So we can imply, hence, P of n is true for all n belongs to n by principle of mathematical induction. That's it. So very simple, and we can easily score 18 marks over here. That's it. And thank you so much for listening. Let's meet in the next series.